Hi. During our last episode, we explored the subject of chemical change. To understand these chemical changes, we have to go deep into the world of atoms and molecules. And as we do so, we must study them with the exactness of science, that is chemistry. Today we will be discussing how we determine the number relationships between particles of reacting substances in terms of a quantity called the mole. We'll also look at chemical formulas, chemical equations, and atomic masses. But before we proceed, let's have a short break. Chemical changes occur naturally or artificially. A chemical change is natural if it is not influenced by man. Take this green leaf, for instance. It is slowly turning brown. The leaves that fall will soon decay and turn into soil. The larva in this cocoon will change into a butterfly. Those roofs are rusting. But a chemical process may also be one that is planned or carried out deliberately. For some of the natural processes, like those you've just seen, chemists can duplicate in the laboratory. How do they do this? First, they must thoroughly understand the principles that govern chemical changes that occur naturally. Sometimes, a chemical change that seems so simple is really complex. It may involve a series of steps. Chemists studying a process strive to determine all possible steps in a chemical change and the order in which they occur from beginning to end. In other words, they first undertake a qualitative study, seeking to answer the question, what chemicals or reactants combine to produce certain products like this? Then comes the quantitative aspects of a chemist's work. They try to answer the question, what are the proper amounts of reactants that must be combined to come up with the desired product? How do chemists determine these quantities? This is a question we will answer today. Meanwhile, let us revisit some basic concepts we have learned. By the 19th century, scientists agreed that all compounds have definite composition. Their constituent elements, or the elements that make them up, are present in a definite mass ratio. Take the compound water. In water, hydrogen and oxygen are present in a 1:8 mass ratio. For every gram of hydrogen, there are 8 grams of oxygen. Or the compound sodium chloride. In sodium chloride, sodium and chlorine are combined in a 1 to 1.54 mass ratio. What about the compound glucose, the fuel of our body, also known as dextrose? Glucose contains hydrogen, carbon, and oxygen in a 1 to 6 to 8 mass ratio. The composition of each compound is fixed, no matter what the source of the compound is. This rule is true for every compound, whether it be benzene, ethanol, or boric acid. These observations are summarized into the law of definite composition. Why does matter behave according to this law? It was an English school teacher, John Dalton, who explained this law with his atomic theory in 1803. He said that atoms are participants in a chemical change. He defined atoms, small, indivisible particles with mass. According to Dalton's theory, all atoms of the same element have the same mass, size, and shape. During chemical reactions, atoms do not change. They are merely rearranged. Dalton also assumed that atoms combine in small whole number ratios when they form compounds. Dalton's atomic theory guided scientists in their studies for more than a century. Since then, some of his assumptions have been modified in the light of new scientific data gathered with the use of more sensitive equipment. Since compounds have definite compositions, they can be represented by chemical formulas such as these. These chemical formulas tell us the kind of element present and the atomic ratio, the ratio of the number of atoms by which the reacting elements combine. Take water. Its chemical formula is H2O. What does this tell us? There are 2 atoms of hydrogen for every atom of oxygen in water. The chemical formula of sodium chloride is NaCl. This means that for sodium chloride, there's 1 atom of sodium for every atom of chlorine. What about glucose? Its formula is C6H12O6. This means that there are 6 atoms of carbon, 12 atoms of hydrogen, and 6 atoms of oxygen in every molecule of glucose. Do you recall what a molecule is? A molecule is the smallest particle of a substance that can exist freely and has all the properties characteristic of that substance. However, this definition is inadequate. The properties of a substance are usually bulk properties. They are so due to collective behavior of an assemblage or big group of particles. Nevertheless, molecules are thought to act as independent units. The chemical formula H2O represents a molecule of water. But for sodium chloride, NaCl represents not a molecule, but a formula unit of the compound. Unlike water molecules, a pair of sodium and chloride ions cannot exist freely in any of its 3 phases. In its solid phase, sodium and chloride ions exist in a crystal structure. In its liquid phase, the sodium ion is separated from the chloride ion. The pair of ions cannot be isolated as an independent unit. In its gas phase, the sodium and chloride ions are even more independent and widely separated from each other. In planning a chemical reaction, it is easier to measure the mass of a group of atoms than to count each atom individually. In the case of marbles, we can see and count them easily. In the case of atoms and molecules, it would be impossible to count them even for a very small sample. Just to give you an idea of how small and numerous atoms are, take this 5 milligram speck of copper. It is made of trillions and trillions of atoms.